David. I'm a research leader for IMEC. If you've never heard of us, IMEC is a R&D hub for nanoelectronics and digital technologies. We are headquartered in Belgium. And one of the many things we do is develop sensor technology. And today I will give you a brief teaser of how, from the AI department, we are trying to support that sensor development. So to give some context to the problem, you might be wondering why we still don't have autonomous vehicles, self-driving cars. For several years now, prototypes of these vehicles have been driving around in San Francisco and other parts of the world. And yet, still, the technology is not mature enough yet to allow consumer adoption. So what is holding these autonomous vehicles back? What are the things that are stopping them? Well, according to law firms in California, which are in a good position to assess this, these are the main causes of accidents with these autonomous vehicles. So these vehicles get in trouble, firstly, because human errors. Other people make mistakes and cause an accident. The second leading cause is that these autonomous vehicles, they misunderstand the intentions of other road users. Specifically, pedestrians and cyclists are hard to predict, and sometimes there is a misjudgment. And the third leading cause is just that the sensors cannot see what they should be seeing to avoid an accident. So this first one is a bit hard to fix because there is always going to be the human element. There's always going to be naughty or stupid people on the roads. What we can do is we can try to empower the perception systems of these autonomous vehicles better so that they can realize sooner that something naughty or stupid is about to happen. For the second problem, it's a similar story. We can work on this from the algorithm side, but also if we would have stronger perception systems, stronger sensors, it would also allow us to better predict what is going to happen. And obviously for the third one, the solution is, well, you need better sensors. So what are the main ways in which sensors are failing right now? We see that the most common conditions for these accidents are when there's adverse weather or adverse light. So we need better sensors. And there's better sensor technology upcoming all the time. And I listed here 3 examples that I care about the most because at IMEC we are developing these. So we are looking into new types of infrared sensors, for example, a quantum dot shortwave infrared camera. Also frequency modulated continuous wave LiDAR, so a solid state LiDAR that can also measure velocities of objects. And also on the radar track, we have some innovations in the pipeline. However, we see that it's difficult to get the market to adopt these new technologies. And the reason that it's so difficult is that car manufacturers and their tier 1 suppliers, they are hesitant to commit to new technology because committing means that you enter a very long and costly, labor-intensive integration, testing, and validation process. So before you commit to this, you really want to know that it's going to deliver you something. And we think that simulation is going to be really instrumental in de-risking these investments and thus accelerating the adoption of these new technologies. Now, simulation, it's not a new thing in automotive. There's actually already a lot going on in that space. But we see that the majority of the currently available software tools for simulation, they stick to the physics. So the strategy is to validate sensors by really modeling the way that these sensors interact with the environment, propagation models, reflection models, really at the signal processing level, seeing what is going on. And this is very trustworthy, but because you need so much detail in this physics modeling, it also means that you will never cover the entire world with this. You cannot cover in such detail the variety and the complexity of real traffic situations. Also, these software packages that you already have, these physics-based models, they exist for current generation technology. But for devices that don't yet exist, for which the spec sheet is still changing, these are not supported by any of these packages. And thirdly, a third shortcoming of this simulation software that is already out there is that if you want to really train a perception stack, they also lack the richness and the environment that you need to train your AI. So these simulation tools that are already there, they don't really answer the question, will my new sensor help us to avoid accidents? And that's where we come in. We want to prove this without relying on these intricate physics-based models. So our dream, our mission, is to start from existing data sets with the current generation sensors and existing simulation software packages. And we want to use generative AI rather than physics-based models to augment these with an extra sensor stream that might as well have come from your real prototype device. So we want to shortcut this physics requirement. And then when we have this, we can evaluate the data set or the simulated data with and without the new sensor technology to quantify the delta that we get through automotive perception and sensor fusion stack. So this is our mission. And this may seem really ambitious, but we are confident that it can be done because we already have some proven work in this space. And I will give the example of long-wave infrared imagers, like a thermal camera. So if you would want to model this from a physics-based perspective, you would need to know the temperature of every little part of every object in the scene to see how much energy it is radiating in the spectrum. Now, this is a difficult problem because we don't know this. Current sensors don't measure this, and you cannot infer this from the camera data, for example. Because to the camera, a cold building and a warm building, it looks the same. But for your thermal camera, it will not. But what we can do is we can create a data set, and it does not have to be a very large data set, of training pairs where we have RGB and a thermal camera together. And if we augment this with segmentation maps that tell us this is a pedestrian, this is a building, this is a car, then we actually succeeded into training generative AI, so style transfer AI, if you like. That is not a one-to-one mapping from RGB to thermal, because, like I said, that doesn't exist, but there's this one-to-many translation, and that can produce representative appearances of thermal camera data without needing to model this temperature. And you see an example on the right. I think it's a powerful example. When you have a row of parked cars, there are two possibilities, basically. Either these cars have been there for a while, so they have cooled down, they look kind of the same temperature as their surroundings, or the vehicle has just parked there, and that means that the tires will be warm, that the tailpipe is warm, the interior of the car is heated for the driver. So you have these two distinct appearances in real data, and we see that our generative AI has learned multiple styles that actually predict that this is going to look either like warm tires or cold tires. So we can now augment RGB data with a thermal data stream that will have the right statistical properties of warm and cold cars because our generative AI was able to differentiate between these cases. If you want to know more about this, by the way, it is also a poster presentation of my colleague Kylie, who is sitting there, who will present this on Wednesday. So do check out the paper if this catches your interest. So we know that we can train these generative AI models if we have the right data. Let's take a look at the other components that we need to make this value assessment of whether your new type of imager will help you. Well, first, as I said, we need some data capture because we need to create the training pairs for this generative AI. Then we can train the models, and then we choose a scenario of interest. For example, here this is generated in the Carla driving simulator where we modeled pedestrians that are haphazardly crossing the road. And then we typically also want to target a specific corner case, like a long tail scenario, in this case, fog that is making your observation more difficult. For this fog-based model, we don't really need AI because it's well understood how different wavelengths of light interact with water droplets of a certain size. So we can model this fully with physics for both the RGB and the infrared camera. And then finally, we need some automotive perception algorithms so we can do the sensor fusion and we can count what can we see and can we now see further, see things sooner, react quicker, locate things with more accuracy. Those are metrics that we are looking for. Here you see a small example. This is a bit of a pipe cleaning exercise that we did. What you see on the top left is what you get from our Carla standard open source driving simulator. And we translated this using the generative AI to near infrared in the second column. So near infrared is not a terribly interesting modality, but it does have the advantage that data sets are already available to train and test this. In the third column, you see a LiDAR point cloud. You don't get the standard from Carla. Well, you get something, but it's not very accurate. We had to spend some effort to also make this a more representative sensor. And Martin, who is also sitting here, will present this as the last speaker in the session. So do stick around for that. And then on the rightmost, you see that we can do object detection and fuse these detections across the modalities and then place these pedestrians on a map. And at the bottom, it's all the same, but now we applied our physics-based model, and that allows us to then compare the results that we get from with or without the near infrared. So when we look at these results, yeah, like I said, it's a bit of kicking in an open door. Near infrared is not a terribly interesting modality. And you can see that here, I'll try to explain the graph real quick. So we have the When it says 2M, it means that we performed sensor fusion of the RGB camera and the LiDAR and their AI. So we use a YOLO V8 model for the RGB camera and center point cloud detector for the LiDAR data. And the 3M, that means that we also added a near-infrared camera, our simulated one, with also a YOLO-based model. And then we see from these curves, yeah, all the graphs, they overlap. So that means that in normal conditions, your sensors, it does not really matter. You don't get anything extra when you have this near-infrared camera. And when we look at the fog situation, we see that this actually persists. So you see that around 30 meters, you lose the pedestrians in your sensor fusion system, with or without this infrared camera. So this is the kind of validation that you want to do to make a value assessment of whether an imager is worth having or not, worth investing in. So in this case, near infrared, if you were planning to invest millions of dollars in that, no, don't do it. Now you can say, oh, how can you be certain about this value assessment? Are you not just evaluating how good your generative AI is? And it's a valid question, because evaluating this is not easy. You could think, yeah, just look at the detection results for real data and simulated data. But we are kind of in a data-starved regime, or we should not be using the simulation. We use simulation because data is scarce, and also because it's a one-to-many problem. We cannot really say in one frame, we missed this guy in the simulated data, and we saw him in the real data, because you might just have chosen the wrong appearance for that. So it's a coincidence. Also, you can ask yourself, shouldn't we be retraining our detection models to really get the most out of our new modality? If you want to get the most out of it, then you will have to adapt the AI, but for that also you need more data. So this is not straightforward. Now, if you look at the academic literature, the way that normally style transfer models are evaluated is using something called Frechet inception distance, FID. And it's quite a neat concept. The idea is that you compute a feature space representation using an inception model. And then you compare the distribution of your values of your feature vector between the real and the generated images. And if these distributions are closely related, if their distance is small, then you know that your generative AI is producing images that are statistically representative of what you are trying to simulate. Now we can also not really use this straight out of the box, because inception is a classification-based model. And for detection problems, it's a slightly different thing. And also, you would really like to fine-tune this towards these corner case scenarios, the difficult cases, the unsolved problems. So we are currently working on gaining some more control on this type of metric. So we can also use this to underpin our confidence in the simulation. Another thing that you could do is you could train a discriminator network that tries to predict whether an image that you feed it is a real, in this case, shortwave infrared image, or it's a simulated one. And if it's really easy to train a discriminator that picks out all the simulated ones, then it means probably that your AI is doing poorly, because there are obvious differences. But also this, you need to qualify it, because on the right you see one of these images is a real shortwave infrared and the other one is simulated. And I think you'll agree with me that the biggest difference is the appearance of these clouds. But we don't care about the clouds. This is quite a large difference in terms of image properties, but it's completely irrelevant for your ability to detect these cars or pedestrians or cyclists. So you also need to really check the results, and this is a manual process to see whether the difference that we observe, whether this metric is really giving us what we need. So also this is a work in progress. You see, it's a bit of a team. We are trying to figure this out as we go along. A final idea, this is something called T-distributed stochastic neighbor embedding. And it's an attempt to represent your feature space. In this case, we have taken bounding boxes from pedestrians over time. And we have computed their YOLO 10 feature space vector. And then we use this T-distributed stochastic neighbor embedding to get a representation where things that are similar, they are close neighbors. You cannot say a lot else about the space except that things that are similar are mapped closely. And this is interesting because this is an experiment where we started from RGB, modality A, and we tried to get this using a training pair to modality B. So B is the real shortwave infrared. And then what is called here fake B, should have called it simulated B. This is the simulated shortwave infrared. And then you see what you really want is that the red curve and the green curve, they are close for these appearances of these pedestrians in feature space. You see, for example, for this case, for this guy, this is the case. This is also not a very important case, because here you see that the RGB data and the sphere data in feature space, they are already quite close. So your camera cannot really, your shortwave infrared is going to be irrelevant in this situation anyway. More interesting is this one here, where you see that now there is actually a large gap between the blue curve and the red curve. So that means that here your shortwave infrared is seeing different features. Your YOLO model is encoding it differently. So here the extra modality makes a difference. And it's very important that here your simulated model is close to the red one and does not stick too close to the blue one. So in this case, you see that it's mostly the case. Just here at the tail, there is some transition effect that can help us to also improve our AI by looking at these cases. So you see there's a lot of different fronts on which we will have to fight this battle to really convince the industry that what we are doing in simulation is trustworthy. Right now we don't have all the answers yet, but we are hopeful that we will succeed in this exercise and get traction for our technology. Now before we finish up, I also want to show you something of our roadmap for non-imager sensors. So other things we are interested in is, like I said, frequency modulated continuous wave LiDAR and radar. So these are sensors that can sense the velocity of objects. They measure it directly by a phase shift. And this is also not something that you get standard out of Carla. So we are building this model, and the first step is to estimate the velocities of parts of objects. I think there's a movie on the next screen. Yeah. So red means something is coming towards you. Blue means it's moving away. And you will see that different body parts of a person have different velocities. And this is exactly what you want, because this is what the sensors, real sensors, what they pick up. So you see here at the bottom, you see a plot. This is the bottom right one. The vertical axis is the range, and the horizontal axis is the velocity that you measure. And you see that these moving pedestrians, they don't really have one velocity, they have like a range of velocities. And this is because I will try to isolate them here. You see here, this is the velocities that you measure isolated around these pedestrians. And you see these repetitive patterns of the swinging arms and legs. And if you're into radar stuff, this is really cool, because this is exactly what we see in real radar data. And we have actually in the past trained AI models that pick up on these patterns to make the distinction between a traffic light and a person, or a trash can and a person. So you can actually leverage this information in your AI models to detect it. And that's really important that we catch this high fidelity. Okay, so I will try to conclude here. So we strongly believe that our generative AI, that we have proven that it has potential to replace parts of these physics-based models for automotive simulation. That this will allow you to de-risk the investment in this technology by having a preliminary value assessment available to you. For this, we have to modify standard AI techniques, because most don't focus on this one-to-many aspect. And this is essential because we don't want to model the physics, but we want to capture the different cases that are the manifestations of this physics in your sensor output stream. And as you can see from the many ideas and lack of results that I presented, it's going to be an uphill battle to convince people that this AI can really be trusted to the extent that physics-based models are right now trusted. And I would welcome everyone to talk to me if you have experience with this, if you have ideas, if I triggered something. If you totally disagree and you don't believe in it, also talk to me. I value your opinion. So find me in the coffee break if you have something to discuss about this. Feedback is always welcome. Thanks for your attention, everyone.